It's an honor to be here speaking to this very distinguished assembly. So the first thing I'd like to do is thank the team that I'm a part of. Since my background's in computer science, it's particularly critical to have the help of people like Jerry and Jill. I wouldn't be here today without them. So, the plan is simple. I want to talk about why we want to do what we're doing, what we're going to build, and how we're going to use it. First thing I want to do is explain why the equation is all funkified. But anyway, I wanted to, despite, I know you lose half the audience every time you display an equation, but this one's really going to take some extra explaining. Basically, I wanted to try to quantify the parameters of a SETI search, talking about what fraction of the sky do you cover with the field of view of your instrument, what fraction of wavelengths are you sensitive to, and of course, fraction implies a total, and the total could be very subjective when it comes to wavelengths. But seeing as most of us are Earth-based, the atmospheric windows seem like an interesting divisor. Fraction of modulations and polarizations you can detect, the brightness with which the signal arrives, the sensitivity of your instrument to detect the signal, the fraction of time you spend observing a target, the fraction of time that the signal is visible to us, and the length of the search program. I want to put some numbers to that, just a few of the dimensions. If you imagine kind of a hypothetical average SETI survey has a field of view of 1 square degree, looks at a target for about a minute before moving on to the next one. Well, that gives you about 20 billion combinations per year that have to be explored. And if that survey operates 365 days a year at night and maybe doesn't have quite perfect weather, then it explores about 1/100,000th of that fraction of the parameter space each year. Then in terms of whether to target a star or not, you don't have to go very far out into the universe before you have quite a lot of stars. At 1,000 light years, the stars tend to be about 3 arc minutes apart, and 1,000 light years is just smaller than the dot used to mark the sun on this map of the galaxy. So with the context that traditional SETI surveys use very sensitive but narrow beams to look at patches of the sky for just a few minutes at a time, and I'm quoting my favorite Optical SETI paper that seems it's altogether reasonable to expect a repetition period on the order of minutes. We wanted to take Avi's advice and go the opposite direction. Can we look at all the sky all the time? We want to do this for a long period of time, at least 5 years. We think we can detect pulses from nanoseconds to hours long, and repetition periods from milliseconds to years. I want to cover the full optical bandwidth and just a shade of the infrared. And you can't see here, but of the 5 of the 6 parameters that you can control of the search equation, we think we do pretty well on. Now, the scenarios we think this is good for, if you're trying to listen in on interplanetary communication, it's probably not going to work out so well. NASA ran a test of transmitting about almost a gigabit between here and the moon using less than a watt laser. And so we're not nearly sensitive enough for that. Interstellar is obviously going to be much brighter, but the problem there is geometry. Space is mostly just that, empty space. And so the chances of intercepting a beam are pretty dim. Beamed energy propulsion, which I have a feeling we're going to be hearing a lot about, has the right properties of being bright enough and transient and last long enough to be detected. We think we do quite well on that. If someone's trying to get our attention on purpose, if they use technology like we have today, take our largest laser and put it into our largest mirror, that's something that we think we could detect from a reasonable distance. Or obviously, if they can focus light even better than that, that would work even better. Natural lasing, I think, is also an interesting scenario. Mars has a natural 10-micron laser, and we're not sensitive in that particular wavelength. But maybe if something else is made to laser or has an appropriate redshift. And lastly, I think it's dangerous to assume we know what ET is doing. And so covering a wide swath of the parameter space is a good strategy. Now, optical, I think, is worth noting, has some advantages relative to radio. Owing to its shorter wavelength, you can focus a much finer beam. As an example, you take a green beam into a 10-meter aperture and point it at the sun from 1,000 light years away, and the beam expands only to be about twice the radius of Mars's orbit. The interstellar medium is quite kind to the color of optical radiation, not so kind to absorbing it. At 1,000 light years, the absorption effect is moderate, but by 10,000 light years, it's getting to be pretty significant. Never goes to 100%, but it gets harder and harder to imagine larger and larger power sources, unless we talk about very large spaceships being propelled to very high speeds. And so lastly, another quote from my favorite paper about how with today's technology, we can outshine our star, our own sun, by a factor of more than 1,000. Now, anyone who wants to get the attention of another species has to exceed the natural background. And so we've theorized and observed many sources that are fast and bright, but we have none theorized operating on a nanosecond timescale. And that's indeed validated by, for instance, Harvard's great work looking at the sky for almost 10 years now. So we call our project AllSat for All Sky All the Time. We started out calling it ASAT, but we didn't want to confuse anybody about building anti-satellite weapons, so we quickly changed the name on that. Any good project, of course, tries to maximize return while minimizing cost. So we limited ourselves to just detecting the signal, trying to localize it to about 1 arc minute spatially, and at best about 10 nanometers spectrally. We want to maximize our coverage and our time on the sky. And of course, you can pick many sensitivities, but we tried to pick the lowest local maximum of sensitivity per dollar. So to that end, we want the largest aperture possible within it. We want a fast readout, and we want to reduce the dynamic range of the sky, bright stars, dark background. That allows us to reduce the shot noise and increase the signal-to-noise ratio and avoid saturation. We have to be able to accurately know where we're pointing on the sky, and we think this gets us something like a nanosecond flash, the equivalent of a 7th magnitude star. For minimizing cost, we need a wide field of view, so of course, large CCD, short focal length. And for minimizing the cost of running the program, you want it to be highly automated and rugged so that nobody spends time babysitting the hardware, the software, or even the data. So here's a schematic of the system. It's pretty simple, actually, just a low-resolution transmission grating in front of a wide-angle lens, in front of a astronomy-grade CCD for high quantum efficiency. There's no tracking mount. We let the sky drift over. The transmission grating allows us to discriminate against any broadband false positive sources, like maybe a satellite glint. And for reading out the CCD, we used time delay and integration, TDI. Normally, one does that, one shifts at the rate that the object that they're imaging is moving, but we drive it as fast as possible to achieve that dynamic range reduction and get our millisecond timing. Then what we do is have a second camera oriented perpendicular and recover that y-axis as well as gain additional statistical confidence in our events. So this isn't just theory, this is a prototype. You can see it's kind of about the size of a funky loaf of bread. The camera's on the bottom, lenses in the middle, and then the transmission grating is embedded in the 3D printed hood there. Now if you were to look through the instrument, this is just a simple schematic view of what you would see. Broadband sources have a 0th order and their spectral orders on the side. But interestingly, the monochromatic source, its spectral lobes are points instead of blobs. And in this case, I've shown it without a 0th order because the transmission grating can do a pretty good job of eliminating the 0th order for some wavelengths. Now, I'm not quite sure how to make this animation play, but I thought it'd be useful to actually watch it work with a night of observation. This is a predecessor instrument. You can see the sky drifting by, you see the clouds, you see some airplanes if you look quickly, and that's the end of that. But as I said, we use TDI, and so those full-frame images are just used for registration. This is more what the system uses for detecting a signal. This is a test with LEDs flashing in the far field. And so it's a little hard to see, but they're all in the same spatial position. That's why their 0 orders are lined up vertically. but they're different color LEDs, and so that's why there's different horizontal spacing to their non-zero spectral orders. But they're firing on regular timing, and that's why their spacing vertically is even. Of course, any sensitive instrument also detects things that you're not interested in detecting, and this is just kind of a sample of cosmic rays, radioactive decay, airplanes, that sort of stuff. Now, a node is half of an observatory. As I said, we have 2 cameras per field of view, so you picture 2 of these for one observatory, one twisted 90 degrees, and this is how we cover the sky. 4 is the minimum number of cameras. Probably 5 would be nice, but as I said, we've tried to design this for the minimum cost, and then we can always scale up later. With each observatory having a field of view of 120 degrees, you need 3 primary observatories per hemisphere. And I don't know if you can see it terribly well. Let's see, we've got a laser. There you go. There's a red dot, there's a red dot, there's a red dot, similarly down here. And so we think this is the minimum to cover the sky, but having secondary observatories is not necessary, but would be quite beneficial. Not only do we get increased statistical confidence and increased coverage on the sky when one site has inclement weather but the other doesn't, but we get this cool spatial validation that we can measure the propagation delay versus the angle of incidence for any co-observed events. We'd quite like to collaborate with people on this. Co-hosting at different facilities would be great, but even better would be working with people who are running existing surveys, particularly ones suitable for Optical SETI, so that we can cross-compare data sets. You could even imagine building something that does real-time follow-up of detected signals, as they are processed in real time. The signal processing, right now we have a heuristic pipeline, and we're planning on building a machine learned version. And there's some cool secondary science we can do with meteor or space debris characterization and triangulation. We think the right way to run a project, of course, is transparently, so all the code is already in the cloud, and we plan on putting the data online publicly accessible. And we'd like to encourage collaboration with all arenas, both academic and with the public, to see what we can do to inspire them on this project. Lastly, to be clear, there's a lot of different bands, a lot of different types of surveys out there, and we think these are all complementary. We should be doing all of this. Maybe we can achieve the all-sky holy grail with all wavelengths in different surveys. So, in case you fell asleep with that first equation, what we want to do is have our 5-year survey, all sky all the time, and we think this puts broad new constraints on the prevalence of bright ET signals. We can do some cool secondary science, and since no one's put an instrument like this on the sky globally for the amount of time, this kind of analysis, we think there's a decent chance for some discovery, and it'll make Avi happy. The instrument itself requires no fundamental new technology. It's low cost, highly automated, that makes it automated and makes it well suited for global deployment and operation. And because it's the first ever true all sky, all the time survey, we think that's pretty high bang for the buck since the cost itself starts out pretty low. But it's really sort of dial a cost, as you can have 6 observatories or 20 observatories. You can have the basic hardware, better hardware. And so we'd love to work with people on that. So if you remember one slide, let it be this one, that whatever ET is doing, if it is bright but intermittent, then narrow, albeit highly sensitive beams are just unlikely to find it. And so we think we should be looking at all the sky all the time. Now with this week's very exciting announcement, I ran the numbers for a 60 gigawatt transmitter, and the system as proposed could detect that from a distance of about 8 light years. For a moderate price increase, we could easily extend that out to 100 light years. Thank you very much. Questions? I can hear you.
Well, I have a question about your point that you want to see, you're looking for bright signatures, and I think you made the point that you want to see this above the background noise. So there are, in RF communications at least, that we know about on Earth, we use forward error correction, nonlinear match filtering, and some other techniques to pull data out of very low gain transmissions. So I wonder, wouldn't someone smarter than we, be doing that same kind of thing and maybe even more sophisticated techniques to pack data into very weak optical signals. So if, are you looking only for, let's say, periodic laser signals, or are you looking also for, let's say, data hidden below the noise floor that you could pull out with some kind of match filter?
Okay, great question. So what kind of signals are we looking for? And basically what we're looking for is power. We're looking for a positive edge and a negative edge. We use a match filter to detect it against the noise as best we can, and that's the first stage of the filtering pipeline. Probably the only thing that doesn't go to machine learning eventually.
So very interesting. I think that in optical SETI, the experiments that I know of that have been designed to get the light, the background light down, there's 3 different ways to get the background light down to where you can detect potential signals. And one way is to just have a lot of pixels on the sky. One way is to do very high resolution spectroscopy to cut the light down, to just look at a small window in the spectrum. And another way is to time slice it to nanosecond or picosecond time intervals. And you kind of combined all 3 of those. And other people have just done like 1 or 2 things, but it's a very interesting idea. But if you combine all 3 of them, of course, you're not doing the super high resolution spectroscopy or nanosecond, but you've got a little bit of each. So I guess my question is, how good is that at getting the background light down? How many counts on each pixel of your CCD do you get in that millisecond time? What's the background rate?
Well, so you're right about the various techniques we're using. The degrees of freedom left to us with the hardware available in order to cover the full sky, we're shifting at about 2 kilohertz. And so the integration time over a column that's 3,000 pixels tall, for instance, is a second or 2. And so we don't, I think we're probably at 1400 ADU in what I've tested, but I'm not testing from a dark site. Modeling suggests that we are pretty sensitive to background light. You really want to be as far away from light pollution as you can. And the contribution between zodiacal light, that sort of thing, versus stars turns out to be pretty close to 50-50. And that's where I've spent a lot of time, is shopping different camera manufacturers. And in fact, I would have brought the system for you to see today, but it is at its manufacturer getting a custom firmware upgrade to make it go that much faster.
Thank you very much. Thanks for being so timely, right?
Thank you very much.